In this lesson, we will present the idea of primitive roots. If we begin with two relatively prime numbers, a and m, then Euler's theorem tells us that a to the power phi of m will be congruent to 1 mod m. A to the power phi of m will be congruent to 1 mod m. So for example, the number 13 is prime, and therefore phi of 13 will just be 12. So any residue that's relatively prime to 13, if I raise it to the power 12, that should be congruent to 1 mod 13. So for example, 3 to the power 12 should equal 1 mod 13. Okay? But actually, there's a smaller power of 3 that also equals 1. Notice that 3 cubed, which is 27, is also congruent to 1 mod 13. Let's look at 2 to the power 12. We know 2 to the power 12 must also be congruent to 1 mod 13. But in fact, there's no smaller power of 2 that will be congruent to 1 mod 13. And 12 is the smallest exponent. It's the smallest power of 2. That is congruent to 1. Mod 13. So we know that if a is relatively prime to m, then a to the phi of m is always going to be congruent to 1. But sometimes there might be a smaller power of the base that is congruent to 1. This leads to the following definition of the order of an integer. So if a and m are relatively prime, then we define the order of a mod m to be the smallest positive integer let's call it h, such that a to the power h is congruent to 1 mod m. So if a and m are relatively prime, we know that a to some power will be congruent to 1 mod m. So phi of m always works. Sometimes that's not the smallest power of A. So we define H to be the order of A if A to the power H is congruent to 1 mod M, and that is the smallest power of A that works. So since H is by definition the smallest positive integer that works, we see that H must be less than or equal to phi of M. But in fact, we'll see that H actually divides phi of M. Okay, so the order of A mod M will actually divide phi of M. Let's look at some examples of orders of elements. So let's look at residues mod 13. Okay, so all the numbers between 1 and 12 are relatively prime to 13, so they all have an inverse mod 13, and therefore each one will have an order mod 13. Let me write out the residues. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, and let's look at the order of these elements mod 13. Well, 1 is already congruent to 1, so the order of 1 is 1. 2, I already said that 2 has order 12 mod 13. You could verify these by just looking at these powers. So look at 2 to the power 12, and you would look at all the smaller powers and see that none of them are congruent to 1 mod 13. The order of 3 is 3. The order of 4 is 6. The order of 5 is 4. The order of 6 is 12. The order of 7 is 12. The order of 8 is 4. The order of 9 is 3. The order of 10 is 6. The order of 11 is 12. And 12 squared is one more than a multiple of 13. So the order of 12 is 2. So look at all these orders. All these orders divide phi of 13, which equals 12. So it's actually a fact, and we'll prove this now, that the order of an element mod M will divide phi of M. So if H is the order of A, mod M, and A to some power B is congruent to 1 mod M, then H divides B. And we know that A to the power phi of M will be congruent to 1 mod M, so therefore H must also divide phi of M. Moreover, H divides phi of M. So we know that A to the H is congruent to 1 mod M. Because H is the order of A, and we're assuming that A to the power B is congruent to 1 mod M. So by the minimality of H, we know that H is less than or equal to B. Because we said that H is the smallest power of A that is congruent to 1, so H is less than or equal to B. Then by the division algorithm, I can divide B by H to write B equals a quotient times H plus a remainder R, where R is greater than or equal to 0 and less than H. So we want to show that R equals 0. So we have 1, which is congruent to a to the b mod m. That equals a to the qh plus r. And then rewriting this as a to the power h raised to the power q times a to the r, we see that a to the h will be congruent to 1. So this is 1 to the power q times a to the r, and this just equals a to the r mod m. So a to the power r is congruent to 1 mod m. But we already assumed that h was the smallest positive power of a that is congruent to 1. And this forces r to be 0. So since r is greater than or equal to 0 and less than h, and h is the smallest positive power of a, congruent to 1 mod m, r must equal 0. Well, if r is 0, then we can write b as q times h, and thus h divides b. So since a to the power phi of m is congruent to 1 mod m by Euler's theorem, we see that h also divides phi of m. This finishes the proof of the theorem. So as a quick corollary, we know that if p is prime, then phi of p will be p minus 1. So if p is prime, the order of a mod p must divide phi of p, which is p minus 1. Okay. So let's look at an example. We know that 31 is prime, and therefore phi of 31 is 30. So if I want to find the order of any element mod 31, the only possible orders would be factors of 30. So let's find the order of 2 mod 31. Well, the order of 2 mod 31 must be a factor of 30. So let's list out the factors of 30. The factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. So these are the only possible orders of any element mod 31. So let's check the powers of 2. Well, if you multiply 2 times 2 times 2 times 2, we see that the first power, that is 1 mod 31, would be 2 to the 5th. By checking powers of 2, we see that 2 to the power 5, which is 32, is congruent to 1 mod 31, and no smaller power of 2 will work. So therefore, the order of 2 mod 31 is 5. So let's go back and look at the residues mod 13. We saw that the order of 2 mod 13 is 12. So the order of 2 mod 13 equals phi of 13. And no smaller power of 2 will be congruent to 1 mod 13. So this gives rise to the definition of a primitive root mod m, which we will define now. If the order of A mod m is phi of m, then A is called a primitive root mod m. So using this terminology, we see that 2 is a primitive root mod 13 because the order of 2 is phi of 13. So the idea is that a to the power phi of m is congruent to 1 mod m, and no smaller power works. Okay. So Euler's theorem tells us that a to the phi of m is congruent to 1 mod m if a and m are relatively prime. And if no smaller power works, then we call a primitive root mod m. So let's go back and look at 2 mod 13. 2 is a primitive root mod 13. But let's look at all the powers of 2. Let's look at the powers of 2 and reduce them mod 13. 2, the first power is going to 2 mod 13. 2 squared is congruent to 4 mod 13. 2 cubed is 8 mod 13. To the fourth power is 16, which is 3 mod 13. To the fifth is congruent to 6 mod 13. To the sixth power is congruent to 12 mod 13. You can verify these. 2 to the seventh power is 11 mod 13. To the eighth power is 9. To the ninth power is 5. To the 10th power is 10. To the 11th power is 7. And to the 12th power, we know, is congruent to 1 mod m. So we can verify that no smaller power of 2 than 2 to the 12th will be congruent to 1 mod 13. But look at all the residues of the powers of 2. If you look at 2 to the power 1 through 2 to the power 12, all of the residues mod 13 are relatively prime to 13, and every single residue mod 13 shows up as a residue of a power of 2. So we see that the powers of 2 to the first power 2 squared up to 2 to the 12th power mod 13 actually forms a reduced residue system mod 13. So this is congruent to 1, 2, all the way up to 12. So the powers of 2 actually form a reduced residue system mod 13. This leads to our next theorem. If A is a primitive root mod m, then the set of powers of A squared, A cubed, up to A to the power phi of m, this set is a reduced residue system mod m. So we need to show that all of these powers of A are mutually incongruent and that each one is relatively prime to m. Well, we know that A and m are relatively prime. So since the GCD of A and m is 1, if I multiply powers of A, if I multiply A times itself, the product will still be relatively prime to m. So we see that the greatest common divisor of any power of A and m must also equal 1. So this is true for any power, any positive power of A. So if k is a natural number, a positive integer, then a to the k will still be relatively prime to m. So all of our elements of our set are relatively prime to m. Now we need to show that they're mutually incongruent. Also, if a to the power r is congruent to a to the power s mod m for some exponents r and s, and we're going to assume that r is greater than 0 and less than or equal to s, and which are both less than or equal to phi of m. Okay, so suppose two elements in this set are congruent, mod m. Then we can divide both sides by a to the r to see that a to the power s minus r will be congruent to 1 mod m. But since s minus r is greater than or equal to 0, and that must be less than phi of m, we see that s minus r can't be positive because the order of a is phi of m. That would contradict the definition of the order of a. So s minus r can't be positive because the order of a is phi of m. So phi of m is the smallest positive power of a that is congruent to 1 mod m. Thus, s minus r equals 0, and s equals r. This shows that the set a squared, a cubed, up to a to the phi of m are all mutually incongruent. So we have a set of phi of m mutually incongruent integers that are all relatively prime to m. Therefore, this is a reduced residue system mod m. So we have a set of phi of m integers that are mutually incongruent that are all relatively prime to m. Therefore, this is a reduced residue system mod m. So our next goal is to show that for any prime number p, there are primitive roots mod p. But before we do that, we need to prove the following theorem. If the order of a mod m is h, and the greatest common divisor of some integer k and h is d, then if we look at a to the power k, this power of k will have order h divided by d. So suppose the order of a to the k is j. Okay. So I want to show that j has to equal h over d. Then a to the k, if I raise that to the power j, that will be congruent to 1 mod m. But the order of a is h, and we have a to another power, a to the power kj, also congruent to 1, so we've shown that h must divide k times j. So we can write k times j as an integer times h. So k times j equals h times b for some integer b. All right. Now I'm going to factor out the greatest common divisor from k and h. So we already said that the greatest common divisor of k and h is d, so I can write k as some integer k1 times d, and I'm going to also write h as h1 times d. So I'm just kind of factoring out the greatest common divisor of k and h. Then replacing k with k1d and h with h1d, we see that k1d times j will be equal to h1d times b, and we can divide both sides by d. So we see that k1 times j equal h1 times b. Thus, from this equation, we see that h1 divides k1j. Well, if we look at h1 and k1, they can't have any factors in common. Otherwise, the greatest common divisor of k and h wouldn't be d. So since the greatest common divisor of h1 and k1 equals the greatest common divisor of h over d and k over d, which equals 1, we see that h1 and k1 are relatively prime, and since h1 is relatively prime to k1 and h1 divides k1 times j, we can conclude that h1 must divide j. Now I want to show that j divides h1, and therefore these integers must be equal. But a to the power k h1 equals a to the h1, and I'm going to rewrite k as k1 times d, and let's rearrange this. H1 times d, that just equals h, so this is a to the h times k1, and we know that a to the power h is congruent to 1 mod m. So a to the power kh1 is congruent to 1 mod m. So this looks like a to the power k raised to the power h1. So therefore, the order of a to the k, which we call j, the order of a to the k, which is j, must divide h1 because a to the k to the h1 power is going to go to 1 mod m. So we've just shown that h1 divides j and that j divides h1. Since h1 divides j and j divides h1, we must have j equals h1, but h1 is, by definition, h divided by d. So we've just shown that if the order of a is h and the greatest common divisor of k and h is d, then the order of a to the k must equal h over d. We will use this theorem in our proof that every prime number has a primitive root.